The last band on this tape was produced as a TV programme, when the course was revised in 1995. 10 years after the discovery of the ozone hole over Antarctica, and just about the time when production of the main culprits, chlorofluorocarbons, or CFCs, was due to be phased out. Unravelling the mystery of the ozone hole has been a formidable task, involving laboratory experiments, measurements in the atmosphere, and the computing power of some of the world's largest and fastest supercomputers. Some of the scientists who've been involved in this ongoing research feature in the video sequence. The narrator is Kiki Waugh.
High above our heads, NASA's Total Ozone Mapping Spectrometer circles the Earth. Processed by computer, the data it collects allow us to visualize the ozone layer in the stratosphere, the shield that protects us from the full intensity of the sun's ultraviolet radiation. The amount of ozone varies naturally from day to day, much like cloud cover lower down. But in the southern hemisphere, something abnormal now happens each spring high above Antarctica.
The appearance of the Antarctic ozone hole was certainly a surprise. We did not anticipate it, neither did anybody else. We were all surprised because originally we were expecting more chemical activity in the warmer stratosphere, and it ended up being the other way around.
The pattern of ozone depletion may have been a surprise, but the culprits, chlorofluorocarbons or CFCs, had been under suspicion for a long time. They were brought on stream in the 1930s as very safe refrigerants. By the early 70s, these compounds were also widely used in aerosol cans. Hundreds of thousands of tons of CFCs were getting into the atmosphere each year. And that prompted Sherry Rowland and Mario Molina to ask some searching questions.
We were aware that there were these industrial chemicals, the CFCs or chlorofluorocarbons, that had been released into the atmosphere and had just recently had been measured, in fact, by Jim Lovelock throughout the globe. And the question was, what happens to these chemicals? They're very stable. What do they react? How do they eventually disappear? So the question that we essentially posed ourselves is, what is the fate in the environment?
They concluded that nothing attacks CFCs in the lower atmosphere, but swept around by winds, the molecules are eventually carried up into the stratosphere. And that takes them into a more hostile environment, because CFCs absorb the short ultraviolet wavelengths that are filtered out by the ozone layer. The higher they get, the more intense the radiation, and the more likely absorption becomes.
The logical conclusion for us was that they would eventually be destroyed in the stratosphere. And that would have been the end of that story, somewhat boring in some sense, except that we wanted to also ask, what are the consequences?
The absorption of UV initiates the breakup of the CFC molecules, releasing chlorine atoms, highly reactive free radical species that can set about turning ozone back into ordinary oxygen. In the process, atomic chlorine is converted into chlorine monoxide and back to chlorine again, so creating a catalytic cycle that can be repeated many thousands of times for each chlorine atom. Multiply that by the huge amounts of CFCs in the lower atmosphere, and you could have a serious problem: possible ozone depletion on a truly global scale.
In the normal atmosphere, there are other processes competing with ozone destruction, and we had to estimate the efficiency of those processes. For example, the chlorine atoms can react with methane to make a very stable hydrogen chloride molecule, a stable reservoir.
That mops up about 70% of the chlorine released from the CFCs. And there is another chlorine reservoir as well, because chlorine monoxide can react with nitrogen dioxide in the atmosphere to form chlorine nitrate. These reactions effectively divert the active ozone-destroying radicals into more benign forms. But research since the discovery of the ozone hole has brought home the lesson that the chlorine locked up in the reservoir molecules is only on hold. In August 1987, the Americans assembled a huge team of scientists at Punta Arenas on the southern tip of Chile. They were equipped with a research aircraft loaded with instrumentation that could probe the composition of the lower stratosphere over Antarctica. Adrian Tuck was there.
The airplane has got a long history. It's called the R2, which stands for Earth Resources 2, and it's a version of the old U-2 spy plane that was originally developed in 1954. The US Air Force has most of them, but NASA acquired 3 through the 1980s. The airplane flies above 95% of the atmosphere, so there's not much air up there to sustain it. The pilots are long-time survivors of high-altitude jet flight, and they've got my greatest admiration, because when we first went down to Punta Arenas, nobody knew what they were going to find, and in fact on the first 2 flights they had to turn back because it was so cold that the fuel was freezing, the jet fuel was freezing.
But over the following weeks, they did make a series of successful flights, taking the aircraft up to an altitude of about 18 kilometers and then heading south towards the pole. Right away, the instrument that detects one of the active chlorine radicals, chlorine monoxide, signaled that the chemistry within the Antarctic Circle was highly perturbed. As this region was entered, the concentration of CLO increased sharply, reaching values about 100 times greater than those at lower latitudes. And there was more to come.
The prize exhibit is the evolution of the chlorine monoxide and ozone traces along the horizontal flight tracks from late August, when the chlorine monoxide was high but the ozone was still near nominal levels. There had been some loss by then, but not very much. By the 16th of September, the chlorine monoxide was still up there at a whole part per billion, and the ozone had been reduced by 40, 50, 60%. And the evolution of that correlation is pretty conclusive proof that it was the chlorine.
Further compelling evidence came with the launch of NASA's Upper Atmosphere Research Satellite, UARS, in September 1991.
NASA's Upper Atmosphere Research Satellite, UARS, is the first mission totally dedicated to investigating change to the upper atmosphere, including processes that lead to ozone depletion. From its vantage point in space, UARS provides near global coverage. This orbit lets instruments distinguish between short-term daily and long-term seasonal effects, and permits a view of ozone depletion over the poles.
The payload includes the Microwave Limb Sounder, or MLS. By detecting the microwave emission from chlorine monoxide, the MLS can monitor the buildup of this active chlorine species. The data for the southern spring of 1992, shown in green, reveals CLO concentrations above 1 part per billion over the whole Antarctic continent and beyond. Run this sequence together with the ozone data for the same time period, and the correlation between high CLO and low ozone is revealed with chilling clarity. But what's so special about Antarctica?
There are a number of very important elements in the very deep ozone destruction that we see in Antarctica. Central to those is the role played by the polar vortex in Antarctica. It's a very strong system of winds containing the air over the Antarctic continent. And this leads to very, very cold temperatures in the Antarctic. Cold enough so that polar stratospheric clouds can form in the very low stratosphere. On these cloud particles, reactions can take place which turn chlorine compounds from relatively benign inactive forms into active forms, chlorine monoxide and the other radicals, which can then destroy ozone when the sunlight returns in a sequence of catalytic cycles.
This sequence of events starts at the end of March, when the sun effectively sets at the South Pole. An area of darkness spreads out within the Antarctic Circle. Up in the stratosphere, the air cools and descends and spins up into a vortex. Feed real meteorological data into a computer and it looks like a cylinder in the stratosphere. The grey surface represents the edge of the vortex, the region where strong winds isolate the air over Antarctica from the rest of the atmosphere. Run the sequence forward in time, and by early May, there's a region in the lower stratosphere, shown in blue, it's about 18 kilometers from the surface, where the temperature has dropped to about minus 80 degrees centigrade, cold enough for icy particles to form. And it stays that cold throughout the winter, and for several weeks after the return of sunlight in late August. In fact, polar stratospheric clouds, or PSCs, persist right through into October, before the vortex eventually decays in the Antarctic summer. And that sets the scene for some unexpected chemistry.
There was really no precedent of ice giving rise to any important chemistry. So we were puzzled at the beginning. But what we had to do is to really try to develop the same type of fundamental understanding that exists for the gas phase.
In Britain, physical chemists at the University of East Anglia are making an important contribution.
Nobody's brought a polar stratospheric cloud back to the lab, and nobody's done a spectroscopic experiment at 18 kilometres. I knew our group at UEA could do something. We were an interdisciplinary physical chemistry section that had the extremes of kinetics and spectroscopy and surface science, and I thought we can contribute here.
What these experiments are designed to do is to simulate the surface chemistry that happens in the stratosphere, the heterogeneous interactions that occur between gas phase molecules and, say, ice particles.
The experimental setup consists of an ultra-high vacuum chamber. 2 ports provide access to an infrared spectrometer and a mass spectrometer. Suspended within the chamber is a gold foil, which can be cooled down with liquid nitrogen or warmed up by passing a current through the wires attached to the foil. A thermocouple monitors the temperature. First, water vapor is introduced, and if the temperature is low enough, it freezes to form a thin layer of ice on the foil. Next, other gases, such as hydrogen chloride or chlorine nitrate, are beamed at the ice surface. What happens when they get there is probed by recording an infrared spectrum of the surface. Then the gold foil is warmed up in stages until the ice film is eventually disrupted. Anything that comes off the surface into the gas phase is monitored by recording the mass spectrum. Recording the infrared spectrum at each stage provides information about the species present at the ice surface, whether they be reactants, intermediates or products.
In retrospect, as I think about our first result in '92, where we deposited molecular HCl onto an ice surface and found no molecules of HCl on the surface, they just ionized quickly and completely, is no surprise really, because any normal chemist who worked in solution would say, well, that's exactly what you're going to get.
These things, they won't react in the gas phase, they don't react in the solid molecular form either, but they will react if one or both of the things on the surface is ions. That's how it looks to us at the moment.
And that could be a clue to how ice promotes the release of molecular chlorine, Cl2, from the reservoir species, a reaction that just doesn't happen in the gas phase. According to the work at UEA, the key thing seems to be the availability of water at the ice surface. When gaseous hydrogen chloride collides with the surface, it interacts with the water and ionizes to give a chloride ion. Similarly, the oxygen of a water molecule attacks the chlorine end of an incoming molecule of chlorine nitrate to produce a positively charged chlorine species, H2OCl+, and a nitrate ion. The next step is more speculative, but a rapid reaction between the 2 chlorine species, one positive and one negative, could well be the process that releases Cl2 into the gas phase. And that's a far less benign form for the chlorine to be in.
Molecular chlorine is an element, a green gas, so that even with a little bit of light, such as what one gets in the spring over Antarctica, this green gas can break apart into chlorine atoms, and those are the ones that then start the same type of free radical chemistry.
So, it's a combination of meteorological and chemical factors that drives the formation of the ozone hole over Antarctica. Given a strong vortex with a frigid core, well laced with PSCs, heterogeneous chemistry effectively removes the normal checks on chlorine-catalyzed ozone destruction. Processed in a different way, the ozone data reveal what happens as the polar night retreats at the end of August. The return of sunlight triggers a very rapid loss of ozone. Within 4 or 5 weeks, virtually all of the ozone in the low stratosphere is wiped out. And it's only the final breakdown of the vortex in summer that permits an influx of warm, ozone-rich air from lower latitudes, allowing a gradual recovery to more normal ozone levels. But what about the northern hemisphere? Adrian Tuck recalls the data that came in from the first field campaign to probe the Arctic vortex in early 1989.
By the first week in February, the chlorine monoxide measurements on the 10th of February anyway, over Greenland, near the center of the Arctic vortex, were actually higher than what we saw in Antarctica. And that showed pretty clearly that even if you didn't have an ozone hole in the Arctic, it was primed for the occurrence of at least substantial ozone loss, simply because the air had been activated.
So why don't we get an ozone hole over the Arctic? The reasons have their root cause in the different distribution of land and sea in the two polar regions. Antarctica is a vast ice-covered continent surrounded by ocean, and that produces a strong circumpolar circulation up in the stratosphere throughout the winter and spring, as we saw earlier. By contrast, the Arctic is an ocean surrounded by continents. During the winter, weather systems in the lower atmosphere push up into the stratosphere, and that has a radical effect on the stability of the Arctic vortex. It's a lot weaker and more distorted than its southern cousin. The air inside it doesn't get as cold, and the whole thing usually breaks down before the polar cap is fully sunlit. And that limits the ozone destruction that can occur in the north.
We have observed ozone decline in the Arctic, but it's nowhere near as deep as is seen in the Antarctic ozone hole. And there are a number of reasons for this. One is that, generally speaking, the temperatures in the Arctic lower stratosphere are several degrees warmer than we find typically in the Antarctic. So we don't see the formation of polar stratospheric clouds so ubiquitously as we do in the Antarctic. What's more, the formation of these clouds tends to be earlier in the season, before sunlight returns. And what we really need are these clouds producing active chlorine, which can then be photochemically acted upon by the sunlight. And we don't see those conditions very often in the Arctic.
But we do sometimes. For example, the northern winter of 1994-95 saw temperatures in the Arctic stratosphere well below average. Fortunately, a major European field campaign, known as SESAM, was underway at the time. John Pyle was one of the main coordinators.
The European campaigns, particularly SESAM, have involved a whole range of activities. We've had people making measurements from a large number of locations from the ground. We've had aircraft flying, 4 research aircraft have flown during the SESAM campaign, making different types of measurements. We've flown large stratospheric balloons capable of carrying scientific payloads of perhaps 500 kilograms up to 30 kilometers. And then we've also used ozone sondes, which are small throwaway devices for measuring ozone, and we've probably flown something like 1,000 of those during the campaign. On top of that, we have the meteorological data, which is essential for both planning the detailed tactics of the campaign and also for the interpretation of the data. And finally, we have a whole stream of numerical modelers who are waiting and trying to use this data in conjunction with the experimentalists. We are capable of putting together models which describe atmospheric transport and atmospheric chemistry, the gas phase chemistry, and the heterogeneous chemistry, the particles, the growth of the particles, the reactions that take place on them. And we have a good, I think, understanding of those various aspects of the system. In particular, what we're now doing are running three-dimensional models, where we put in the gory detail of the three-dimensional atmospheric transport. And we can do that by taking information from the weather services. So they essentially can tell us what the winds are, and we can use those to blow the chemicals around in our numerical models. And they've been proving remarkably successful in interpreting data that we've collected in recent campaigns.
Back in Cambridge, other members of the group have used the results from their 3D model to make a movie of the way chlorine monoxide evolved during the winter of 94-95. Enhanced amounts of CLO show up as a murky green blob contained within the Arctic vortex. It's already there when the simulation starts in late November 94. 2 weeks later, heterogeneous processing by PSCs has produced an inner region, shown in the more solid colour, which is full of highly activated air. Moving on into January 95, the vortex becomes very distorted, pushing a mass of processed air down over the United Kingdom. And that's just what the experimentalists saw as well, because in late January, measurements from the ground detected very high levels of chlorine monoxide over the north of Scotland. Speeding on through January and February, notice the contortions of the vortex and the way blobs of activated air peel off to lower latitudes. But this is the most telling point. In most winters, the high CLO has decayed away by the end of February, but it persisted until late March in the cold spring of 1995. And that brought us as close to having an ozone hole in the north as we've ever been.
From all the ozone measurements that we have from the ground, from the aircraft, from these ozone sondes, we have seen absolutely without doubt evidence of a substantial ozone decline within the Arctic polar vortex. And we think that decline has been probably as much as 50%.
Arctic weather patterns may save us from the kind of deep ozone holes seen in the south. But even so, it's clear that an unusually cold winter and spring can trigger short periods when northern levels fall dramatically. The conditions in early 1995 were probably the result of natural variability. But what of the future?
A number of things can cause cooling of the lower stratosphere, and one of those is removal of ozone itself. We see this in the Antarctic when, having formed an ozone hole, it now appears that the vortex is more stable probably than it used to be. It takes a little bit longer for the vortex to break down because, having removed ozone, we don't that ozone deficit can't then absorb radiation and heat up the stratosphere.
And the longer the vortex stays around, the more chance there is for the chemistry to do its work. So if the Arctic vortex is going to start surviving well into March and April, then we could well see more severe ozone loss in the north. But the single most important factor in the years to come will be the amount of chlorine getting up into the stratosphere. Under the terms of the Montreal Protocol, CFCs and other chlorinated compounds have now been phased out. Even so, it's going to take some time to nurse the ozone layer back to health.
We certainly don't expect things to get better until early in the next century. Thereafter, of course, as these compounds are removed, then things should get better. The best modern calculations, however, suggest that there'll still be an ozone hole, at least until the middle of the next century.